All right, so we're going to take a look at integration with substitution. And to do that, we have to go back into Calculus 1 and consider the chain rule for Calc 1. So the chain rule, what it said is if you were taking the derivative of a function and there was another function living inside of it, then you would take the derivative of the outer function, leaving the inner function exactly where it was, and you would multiply by the derivative of the inner function. Now, taking this in reverse, if we have this particular thing right here, then the original function, oops, switch color, go over here, is an antiderivative. Of the derivative over there, right? Antiderivative is just the backwards. So for example, let's take the derivative with respect to x of the sine of x squared. Its derivative is the cosine of x squared, right? I take the derivative of the outer function, leave the inner alone, and then I multiply by the derivative of the inner function, 2x. So now, if I wanted to find an antiderivative of the cosine of x squared times 2x, that would be the sine of x squared. So as far as an indefinite integral goes, so if we were integrating with respect to x, oops, premature, the function cosine of x squared times 2x dx, an antiderivative for that would be the sine of x squared. And since we didn't have bounds of integration, that's indefinite integral, we have to do a little plus c there. So there could have been anything added on. I started with nothing added on, but c could be something else. Again, because if this direction is a derivative, the other direction is an antiderivative. Now, what we're going to do to tweak this is we're just going to say, we talked about U-substitutions a little bit last term. So in this case, I could say, well, here I have the cosine of u, and then the derivative of u in differential form is right there. And so we can call that du. Okay, so just a little side note on that to clarify, if I let u equal x squared, then du dx is equal to 2x. And then if I write this in differential form, which we did a little bit last term, du would be equal to 2x dx. So what I'm doing here is I'm doing a substitution and saying, hey, instead of x squared, I'm calling it u. So then du would be 2x dx. And so here's my du, there's my 2x dx. And that's the chain rule gives the idea of integration by substitution. So let's just look at another problem. So new page. Suppose I had to take, switch color again, the integral of x squared minus 3 to the, I don't know, 4th power, and then times 2x dx. So that's a pretty complicated function there. But I see a 2x here, I see x squared here, I see a 2x outside, so then I'm going to do a u substitution on this to try and simplify it. I'm going to say, all right, let's let u equal, I'm going to choose the whole x squared minus 3 to be my u. And if I take the derivative of that, my du is going to be 2x, derivative of minus 3 is 0, and then I'm going to put the dx right next to it here. So write that in differential form. So then I apply my substitution. So anywhere I see an x squared minus 3, I'm going to replace it with a u, and anywhere I see a 2x dx, I can replace that with du. So now I can rewrite this integral as u to the 4th power, and then this whole thing right here is my du. Hey, that looks way easier. And we have an antiderivative rule for that, right? The power is going to increase by 1, so that's going to be a u to the 5th. And then I have to multiply by 1/5 or divide by 5, whatever your preference is. And we have our plus c hanging out. And then what I do is I back substitute. I bring my u back in. So let's switch colors here. So now I have that the original integral must be equal to parentheses x squared minus 3 raised to the 5th power over 5 plus c. Now, you may think this was kind of confusing, or maybe this looked too easy. You know, we can always check these by differentiating. So I'm going to throw a little check in here. So if I take the derivative with respect to x, and derivative of a constant 0, so I'm going to ignore that, of x squared minus 3 raised to the 5th over 5. The divide by 5 is just a constant, so I can just, hang on to that. So I'm just going to leave it there. The derivative of this involves the chain rule. The outer function is the 5th power. So that would give me 5. Leave the base alone for a minute. That's the inner function. Reduce that power by 1. Then I have to multiply that by the derivative of the inside, and the derivative of x squared minus 3 is just 2x. And then this cleans up a bit. The 5's divide out, leaving x squared minus 3 to the 4th power times 2x, which is the integrand that I started with up there. So it does check out. So this is called integration by substitution. And does it always work? Answer is no. It doesn't always work. So let's look at an example where it doesn't work. New page. So suppose I wanted to find the antiderivative of the natural log of x cubed with respect to x. So this one's a little tricky because I have a function within a function. And so in this case, I'd say, all right, well, maybe my u should be x cubed. If that's the case, then du would be 3x squared dx. Problem, I don't have a 3x squared out there. So my substitution is not going to work. Now, you may say, hey, well, we could just, solve for dx, perhaps. So if I try that, I'm going to get du divided by 3x squared equals dx. And then when I try to do my substitution, I'm going to get the integral of the natural log of u, because u is my x cubed, and then the dx gets replaced by du over 3x squared. But the problem here is that now I have u's and x's. That's 2 variables in the integral, and this is a mess. And so that is not helpful. Okay, so because this x term was missing, that was a problem. So I need another technique for that. All right, let's do another one. Let's try the integral of the cosine of 3x. So here I have a function within a function. So I'm going to use a U-substitution. And I'm going to let u equal 3x. So then du is just 3 dx. Now, I don't have a 3 over there, but I'm going to pull that trick I did before. I can take that 3 over the other side so that dx is 1/3 of du. Now check out the substitution. So now if I take the integral, cosine 3x gets replaced by a u, and then the dx gets replaced by a 1/3 du. And the 1/3 is just a constant. That's going to move to the outside. So I'm going to have 1/3 times. And then antiderivative of cosine would be the sine of u. No problem there. And then I have my plus c after that. Okay, double check. What's the derivative of the sine? It's the cosine, and the 1/3 just gets carried along as a multiple. To get our answer to the original problem, we just back substitute here. So then this would be equal to, for the original one, 1/3 that's a 3, times the sine of 3x. And because it's doesn't have boundaries, it's an indefinite integral, I have to not forget my plus c. So that'd be the final answer based on my substitution. All right, let's try another one. New page. Suppose I had the integral of x times x squared minus 4 raised to the power 1/2, so square root of that with respect to x. And I want to find an antiderivative. So this is pretty complicated. I have a function times a function, and that function involves a function of a function. So U-substitution to try and make this simpler. So usually it's the inner function here that you want to try for your u. So let's let u equal x squared minus 4. Du then would be 2x dx. And a couple ways to think about that. We could do a little algebra kind of jiggery-pokery with the du dx. Another trick we could apply is to say, well, you know, I'd like to be able to find a 2x dx, so I could just throw a 2 in here, and then I could compensate by multiplying by 1/2 outside. Then in this case, I can get both my du in there, and I just have to tweak by adjusting by a constant. So there's a couple of approaches one can take. So continuing my substitution, I have the 1/2 chilling outside. 2x dx becomes my du. And now I have, this is just my u to the power 1/2. Antiderivative, the 1/2 is hanging out, so I'm going to leave that out front. I increase this power by 1, so 1 plus 1/2 would be 3/2. And then I divide by 3/2, which is like multiplying by 2/3. And then I have my plus c. Constants clean up a little bit here. Whoa, crazy pen. Switch colors again. So then 1/2 of 2/3 is 1/3. Replace the u with what it originally was. Power is now 3/2 and then plus c. So that should be the antiderivative of that original function in black up here. All right. Let's try another one. So new page. Let's do a definite integral. And there's a couple ways to deal with a definite integral, so we'll look at it both ways. Suppose I had the integral from 0 to 1 of x squared times 1 plus 2x cubed to the power 5 with respect to x. So at first I ignore the boundaries and I apply my substitution. So here I have a lot of crazy stuff, and usually the substitution is an inner function. So an inner function here would be 1 plus 2x cubed. So I'm going to give it a try. Is it possible you choose the wrong function? Yes. And then as you substitute, you'll see something's not going right, and you can try a different way. So then du is going to be 3 times 2 is 6, x squared dx. Looking back here, I can see the dx and the x squared. The 6 is missing. So one possible option is to multiply in the 6 here, and then multiply by 1/6 there. So 1/6 of 6 is 1. I haven't really changed anything, but now I have what I need for my u substitution. One problem now is I'm going to skip the boundaries for a moment and just throw in my substitution. So 1/6, and let's see, this and this is my du, and then the parentheses are my u. So this cleaned up dramatically from what it was before. Ooh. Now, one problem with the boundaries is these black boundaries up here, those are x values. So up top here, oh, my pen, there you go. These are x equals 0 to 1. Now I have u. So there's two ways to proceed. One way is find the antiderivative, reverse substitute, and then deal with the boundaries. The other way is to rewrite the boundaries. So I'm going to do it like I did the previous problems. I'm just going to come up here. I'm going to continue with ignoring the boundaries and do an indefinite integral. 1/6 hangs out. And then I'm going to have, let's see, increase the power by 1. And then I'm going, oops, increase by 1. There we go. And then divide by that power. Let's see, in this case, I have a big constant. So for my antiderivative, I get 1/36th when I clean this up a little bit. U is really 1 plus 2x cubed to the power 6, and the plus c. Now, next step, I have to deal with the boundaries. So then I'm just going to wrap this in square brackets. I'm going to write the original boundaries back in because I'm back to x's, right? And so then I just plow through here, plug in my upper boundary. So I'll have 1/36th times 1 plus 2 times 1 cubed. Let's see, that goes in parentheses to the 6th, and then minus, and notice I just pulled the 1/36th out of all this. So I'll deal with that after, and then I'll have 1 plus 2 times 0 cubed raised to the 6th. Cleaning this inside up here, I get what? 3 to the 6th power minus 1 to the 6th power, and 3 to the 6th power is off my calculator radar, so I'll clean that up in a minute. And I have 1/36 times that. So let's see, calculator. Bring up a web page here, and we'll say go to google.com. And what is 3 raised to the 6th? It's 729. Okay. So back to the board here. So I get 1/36 times 729 minus 1, which is 728. And then that's going to reduce a little bit, but there's my rough answer. Now, alternative would be to rewrite these units right away. So let's go, whoa, new page. So I had the integral from 0 to 1 of x squared times 1 plus 2x cubed to the power 5 dx. And we did our U-substitutions. I'm just going to repeat that quickly. If u is 1 plus 2x cubed, then du is equal to 6x squared dx. Oh, crazy pen. So then I chose to put a 6 here and a 1/6 outside. So that gave me the integral 1/6 times that of u to the 5th. All right, so from here, there's another route. So these original boundaries were x equals 0 to 1. I'm going to rewrite those as u boundaries. So if x was equal to 0, then u would be 1 plus 2 times 0 cubed, which is 1. So here I'm going to let u go from 1. And if x was equal to, oops, I should write that down, then u would be 1 plus 2 times 1 cubed, which is 3. So u is going to go from 1 to 3. So I can just, bypass these going with x. And soon. So then from here, I have 1/6 times the antiderivative of u to the fifth, which is u to the sixth over 6. And then I'm evaluating that from 1 to 3. So that's going to give me 1 6 times 1 6. So let's pull the 1/36 out. And then I'm going to have a 3 to the 6th minus 3 to the 1st, which is what I had before. So 1/36 times 729 minus 1. And so I get 728 over 36, which you could reduce if you want to. But that's the same answer I had before. So if you're doing a definite integral, you have two options. You can switch the boundaries from x to u, and then you don't have to reverse substitute, but you do have to calculate those boundaries. Or you can do the reverse substitution and plug in the original boundaries. So you just always need to proceed with caution with a substitution and a definite integral. That's it for now. I'll catch you in the future in math.